All right, today we will study the conic sections in polar coordinate. So last time we talked about the conic sections and their optical properties. Okay, how light is reflected on these conic sections. Now we already know that these curves have really nice properties, optical properties. Okay, such as, for instance, we mentioned that the parabola, we can use parabola to design the autolight. And we also have this kind of ellipse and hyperbola. Okay, they have really nice property when light is, towards one of the focus. Okay, towards one of the focus. Okay. Now, this section we will study the conic sections in polar coordinate. Okay. Now we will derive the polar coordinate of these conic sections. The following theorem. So we have the three cases for conic sections: parabola, ellipse, and hyperbola. And use polar coordinate, we can give a universal declaration. Okay, universally, okay, unify all three cases in polar coordinate. Okay, so the theorem says the following. So let F be a fixed point. Called the focus. And L, let the line L be a fixed line called the directrix. Directrix. Let E be a real number, positive number, be a fixed number. Then we consider the following problem. We study the set of points such that study this set, the set of points P on a plane. Okay, in XY plane, in the plane. Okay, in the plane. Okay, such as PF over PL is E. Okay, the ratio of the line of the point to a point over the ratio of the point to a line is E. Okay, now the set of points in the plane. Okay, here the point and the L, the plane is the plane is determined by the point F and the line F and the line L. Okay. Now, of course, F and L is not on the line L. So the set of points satisfies this ratio is E, is a conic curve, is a conic section, is a conic section. And the conic is okay, A if E is less than 1. An ellipse. If E is less than 1. B, a parabola. if E equal to 1. And C is a hyperbola if E is greater than 1. Okay. Okay, the proof of this theorem is actually the main work that we should do actually to determine the conic section, the polar coordinate form of conic sections. Okay, now let's do it. Now we want a fixed point F and we want a line L. And then so suppose now we put some suppose this x-axis here. Now suppose this y-axis. Now to make our life easier, we choose F as the origin O. Okay, F, and then we choose the line L here. L. Okay, such that this part is D. Okay, the distance of F to the line L is distance D. Now suppose we want to find PF over PL is E. Okay, the ratio is E. So suppose PF. Now let's suppose E is less than 1. Assume E is less than 1. So we should get an ellipse. Okay, so now PF over PL is E less than 1. So suppose it's P here. PF and then PL. So the distance PL is this. Okay. Okay, suppose this x-axis, then this angle is theta. So we need to find the relation between theta and R. So this is R, okay? So P is, R theta. Okay, polar coordinate. So we want to find a relation between R and theta. Okay. Now what do we get for PL? What do we get for PL? Okay, so PF is easy. PF is R. Now how do we get a PL? How do we get a PL? So this is this part. So if we do perpendicular line, this part is R times cosine theta, x coordinate. Okay, then the total is D. So PL is the total distance, which is D. Okay, subtract. Let's this point be Q. Subtract FQ. Now FQ is R cosine theta. R cosine theta. Okay, R cosine theta. Then we can get this should be R equal to D minus R cosine theta. Okay, this should be the ratio is E. Okay, the ratio is E. So this we get the relation between R and theta. So this we get R multiply the denominator E times D minus R cosine theta. Okay, which will be E times D minus ER cosine theta. And then move the terms that has R to one side. So it's R plus ER cosine theta is ED. So the R factor of R, 1 plus E cosine theta, which is the ED. Okay. So this we get so this we get R equal to ED over 1 plus E cosine theta. Okay, so this polar coordinate, polar. So this is the polar coordinate of the curve determined by P. Now let's find the Cartesian coordinate. Okay, Cartesian coordinate, and see how this is determined. Its Cartesian coordinate form. Okay, find its Cartesian coordinate. Okay, now let's find its Cartesian coordinate. Now from this step, it's easier actually to do this step, Cartesian coordinate. Then we get r squared equal to, how do we get the Cartesian coordinate? E squared d minus r cosine theta squared. So Cartesian coordinate, so we will explain why this curve is actually Conic section. So we just find its Cartesian coordinate, what this curve is in Cartesian coordinate. So this will be r squared will be x squared plus y squared, no problem. Now r cosine theta, which is just x. Then we expand this. D squared minus 2dx plus x squared. So this will be e squared d squared minus 2d e squared x plus e squared x squared. Then finally we do something. We do some algebra. Okay. So this will be put the degree 2 terms. So e squared x squared move to the other side. Then we get y minus e squared x squared. Now y squared has only y squared. Oh, sorry, we don't forget this degree 1 term of x. 2d e squared x move to the other side, and then y squared, which is the right side, is e squared d squared. And then we complete the square. So divide y minus e squared. So suppose if e is not you see, if e is 1, then we get this. We get 2d x squared plus y squared is d squared, which is this gives us a parabola. This is an equation of parabola. Okay, parabola. Okay, remember parabola is a quadratic curve. Okay, so in this case we get a 2d and you see parabola. Then we get a parabola. It's not centered at origin O, so we need to do some a little translation. Okay, we need to do some a little translation. Remember, the general thing is parabola. We get a 4p x equals y squared. This is x equals y squared. So x is y squared. It looks like this. P is positive here. So this is p. This directrix is negative p. Okay, so we get this thing. Okay. Then here we need to do some translation. Then we actually get that. It's not big. It's not difficult to actually find this. Yeah, actually this thing, you see, what we get, the directrix is, this is d, this d. Then what we get is this thing should translate the curve to the by 2p. So here if you compare, then you get a d, 2d is 4p. So p is 1/2 of d. Okay. Then you should translate the thing so that we get the directrix should be coordinate d. Okay, coordinate d. Okay, just translation. So this gives us the case when e is 1. Okay, when e is 1. This indeed is a parabola, conic section. Now when e is, let's see if e is less than 1. If e is from 0 to 1, e is positive, remember. Then what we do is we deal with this equation. Okay, let me just copy it down here. So this is y minus e squared x squared plus 2d e squared x plus y squared is e squared d squared. And then we just complete the square. Then claim this is actually an ellipse. So this will be divided both sides by 1 minus e squared. So this x squared plus 2d e squared y minus e squared x plus y minus e squared y squared with e squared d squared. Now complete the square. Remember the standard equation of conic section of ellipse is of this form, standard form. X squared over a squared plus y squared over b squared is 1. So standard form, centered at the origin O. But here we need to complete square and then move it around. So it's not naturally centered at O. not the natural center at all. Because here, by our choice of F, the F is the focus. Now, by our choice of F, the focus is centered at the origin O. So here we need to translate it properly so that we get the right equation. So we complete square. This we get x minus x plus half of the degree 1 coefficients, half of the coefficient of degree 1 term. So this will be 2 cancel out. So it's 1 minus a squared, perfect squared, plus y squared minus e squared. But we, by counting the square, we actually add some extra thing. Then the right side is e squared, d squared, y minus e squared. And then we should subtract. What we subtract is we add the thing. D squared, e squared, squared. Now this comes from the term, the actual term when we complete the square. Okay, complete constant term when we complete the square. And then if you what do you finally get? This will be the right side. What we get is this thing. If you the right side, we get e squared d squared y minus e squared plus d squared e to the power 4 y minus e squared squared. So if you factor out the common factor, so this is d squared e squared y minus e squared, and then this is the 1 plus the remaining thing is e squared here, y minus e squared. So this is the remaining thing. Now if you use common denominator, so it's d squared e squared. No, this is exactly y minus e squared. Okay, so this will be d squared e squared y minus e squared squared. So finally, this will be let this thing be h squared. Let this thing be h squared. So let h be d e squared y minus e squared. Okay, now the equation becomes what do you get? Okay, so this will be x plus h squared. Okay, here h is positive. Yeah. Yeah. Did I get something wrong? Oh, wait a second. Did I get a sign mistake? This is, let's see. Yeah, this is correct. This is correct. This is correct. Then what we get is x plus h squared over. So this thing will be x plus h squared plus y squared or y minus e squared. The thing will be h squared. Okay, so this will be, if you divide, so this is x plus h squared over h squared plus y squared over h squared y minus e squared, which is 1. So if you choose a squared to be h squared, b squared to be h squared y minus e squared. Remember, y minus e squared is positive. E squared is less than 1. So this is positive. So so this will be h squared will be d squared e squared. So remember, h is the thing, y minus e squared times y minus e. So this will be d squared e power 4 over y minus e squared. So here a, by our choice a is h, e squared d over y minus e squared. And then this will be, b will be d e squared over square root of 1 minus e squared. Okay. Okay. Then you can also solve for c squared. Remember, c squared in this case is a squared minus b squared. So this will be a squared will be e power 4 d squared y minus e squared minus b squared y minus e squared d squared e to the power 4. So this will be exactly, if you factor out common factor, so it's e squared e power 4 y minus e squared y minus e squared minus 1. So this will be what we get is what do we get? Wait a second. So this what do we get is d squared e 4 y minus e squared. So this we get sorry. The other way around. Yeah, this is correct. This actually we get e squared y minus e squared. Yeah, that's correct. Try to use common denominator, then we get that thing. Okay, use common denominator, we get that thing. So this we get d squared e to the 6 y minus e squared. So c will be d e to the 3 y minus e squared. Okay. So you see, A is, by our choice of A is d e squared y minus e squared. So you see, if you divide C divided by A, use a lot of cancellation, then you get exact E. Okay. So the definition, the E is the ratio of this distance F, PF over PL. Okay. So this thing, the constant E is called eccentricity. So this E is called eccentricity. Okay, for the ellipse, this E is less than 1. Okay, so you see, we get an equation of an ellipse. Okay, we already find its A, B, C, its parameters, and it's now we know it's not centered at the origin O. It's translation along the x-axis. Okay, translating by each unit. Okay, so this is the case when E is less than 1. Okay, now it remaining the case when E is greater than 1. Okay, if E is greater than 1, what happens? The remaining case, if E greater than 1, then what do we get? Now the completing square is still true. The completion of the square is still true. Okay. Then what we get is remember this, the completion of square doesn't depend on our choice. Okay. We don't use anything about this constant E. Okay, whether it's greater than 1 or less than 1. So this is still true. But the other thing is, so if you write down the equation, if you let me copy the equation. Okay, copy down the equation. So this will be x plus e squared d over y minus e squared plus y squared y minus e squared. And this will be h squared. So this will be h squared. Sorry. Now, if you see, this is the equation that we get. This is the Cartesian coordinate that we get. Now, you see, if e squared is greater than 1, then the coefficients, then h squared minus e squared is less than 1. So we can write anything as negative squared as negative b squared. Then we get b squared equal to h squared e squared minus 1. And then this will be of the form x plus h over a squared minus y squared over b squared is 1. So this is actually the hyperbola, equation of the hyperbola. But it's not centered at 0, 0, 0. Okay, it's translated by h. Okay. Okay, now we can conclude that now we can have a universal description of the three cases simultaneously. That's really nice. Ellipse, parabola, and the hyperbola. So we can use polar coordinate, then we can describe the thing universally, use one equation. That's good. Okay. Then according to what we just did, then we can write its polar equation as theorem, as this form. A polar coordinate, a polar equation of the form R equal to this thing, ED over 1 plus E cosine theta. Okay, now remember when we have polar coordinate, we can rotate the thing by any angle. Okay, we can rotate it by any angle. So if you rotate the thing by pi over 2 or plus minus pi over 2, then sine will become cosine will become sine. Okay, plus minus. Or if you rotate the thing by pi, then cosine theta, you get a negative cosine theta. So actually you get a plus minus the thing, or you get rotated it by pi over 2. Plus minus e sine theta. You get this equation, okay? This is actually represent a polar coordinate, polar equations of Conic sections. The thing, okay, because we can rotate it, our angle theta by any angle, okay, so that we can choose something rotation by pi or pi over 2. Okay, so we get this kind of represents a conic section. The thing represents a conic section. With E, okay, eccentricity E. The conic section is an ellipse. Is an ellipse. If E is less than 1, now E is positive, okay, a parabola. If E equal to 1, and a hyperbola if E equal to greater than 1. Okay, let's see some examples. Okay. Now let me give maybe a remark. This polar equation of this Conic sections actually plays a really important role in the development of mathematics in history. Here is some history. You know, astronomers study the laws of the universe. They actually want to, for instance, they look at the position of the stars. They look at the position in the stars. You know, maybe I should mention this Tycho. Remark, digression, maybe digression. This Tycho. Tycho. Now, Tycho is a nobleman. Dennis nobleman. Then he was the last astronomer that actually observed the star by naked eyes. It is said that Tycho has really good eyesight. He was the last astronomer that observed by naked eyes. And then, because the invention of this telescopes, like you see Galileo Galilei. Now Galileo Galilei know how to produce telescopes from glass. Now Tycho observed this. He got a lot of data about the position of the stars. Actually, he and his assistant Kepler, they produced the first map of the stars in the position of the stars. They have a lot data. And then when Tycho died, this data was given to the copyright of the data given to probably Tycho's son-in-law. However, Kepler used this kind of data actually get his famous law, Kepler's law. Okay, Kepler's law. He got three laws. He gets three laws, which is Kepler's. So they are not. So the three laws was not discovered in the same period, in the same time. So there are like several years between them, like 8 years or something. Kepler's law says the following. So three laws says, first law says a planet revolves around the sun in an elliptical orbit. Orbit with the sun at one focus. And the second law says the lines. So if we explain this, if we have an ellipse, then the sun, the orbit of a planet around the sun is actually an ellipse. Okay, an ellipse. Then the sun is at one of its focus. Okay, one focus. Then, so here suppose this is the Earth, and then this is the sun. So we just view them as particle. Forget about their size. Then this thing is okay. R is theta, a function of theta. So here R is a function of theta. So this is theta. Now here, so it travels along this curve. Now in unit term, the radius, the line segment, okay, between the Earth and the sun, will swaps out equal area in equal terms. Okay, this is the second law. The lines join the sun to the planet or to the Earth, swaps out equal area, areas in equal terms. Okay, now here you see the radius has the largest radius and it has the smallest radius. So the position when the Earth or the planet that is closest to the sun is called perihelion. Okay, this thing, this position is called the perihelion. Perihelion. And then the furthest point is called, this point is called aphelion. Okay, aphelion. The shortest point is called perihelion. Okay, you see, at this perihelion, this thing, the velocity is bigger. Okay, but then at this aphelion, the velocity is smaller. So that they should, swap out equal area in equal terms. Okay, because if for bigger readers, then it should travel slow. For small readers, then it should travel fast, so that they can actually get swept out equal area in equal term. Okay, the third law says t squared over a squared, a cube is constant. For all planet that travels along the sun, where t is the period, of a revolution. Now for the Earth, what is t? The Earth travels around the sun one time. How long does it take? Now it takes this definition of a year. Okay, what is the definition of a year? The time that the Earth travels around the sun for once. Okay, once. Okay. Now you see, if the A is the parameter, A is the length of the major axis. A is the parameter A for this ellipse, and the parameter A is the length or half length the major axis of its orbit. Okay, or half of that thing. It's not a big deal. Okay, now let's see some data. Okay, can everyone see the data? The data used by Kepler, so this come from Wikipedia. You see, for this planet, you see r cube over, so we did it backwards. R cube over, you see r cube over t squared is, you see the right side is actually really looks like a constant, looks like really constant. Now you see for the period of the Earth, you see, we have 365.25. Okay, this is actually, you see, it's not exactly 365 days. Okay, so it's some extra. There are some extra near a quarter days. So this is why we have an extra day every 4 years. Okay, so that this extra day every 4 years we put in February. Okay, so we get February 29 every 4 years. Okay, now this is not exactly a quarter days. Okay, it's slightly less than a quarter days. So this is why we every century, every 4 centuries, every 100 century, if we do that manner, every 100 century we should subtract 1 day. So this is slightly less than a quarter days. Okay, you see what this Kepler wrote upon finding this pattern Kepler. I first believed I was dreaming, but it is absolutely certain and exact that the ratio which exists between the period of time of any two planets is precisely the ratio of the 3/2 of the power of the mean distance. Okay, now let's go back to our OneNote. Okay, now let me mention a little bit how the discovery of Kepler's law. Kepler, it takes a long time actually to get this Kepler's law from the data. Kepler's law from this data. Kepler's law from the data. And also there's some copyright issue between the copyright of the data was believed to given to Tycho's son-in-law. Okay, now Kepler's law, let me do some remark. Kepler's law is based on experiment. It was said that Tycho and Kepler, they come up with 21 models of the curve of the orbit of a planet. And somehow they eliminated 20 of them, but then they find one of them agree very well, which is the ellipse. Okay, they find that the ellipse agree very well with the orbit of the thing. So they conclude Kepler's law. So it's based on experiment. So Kepler get this rule from observation of this data, but he does not understand why the planet should satisfy this law. Okay, so it's based on experiment, purely experiment. So he cannot find another principle that explains this. And then within 70 years, so after Kepler gave his 3 laws, then nobody know why the orbit should be an ellipse. And then it should wait for another genius, i.e. Isaac Newton. Okay, it should wait 70 years. It was until 70 years later. 70 years later, that Isaac Newton, explained Kepler's law. Kepler's law. Three laws. Kepler's 3 laws by his theory, his gravity theory, his theory of gravities. Gravity theory, universal gravity. Okay, gravity theory. Okay, now Newton assumed that his universal gravity, F, is the gravity force between 2 objects with distance r. So suppose we have distance capital M. So suppose we have object capital M and little m. They have distance r. So then the gravity between them is some universal constant, capital M, little m over r squared, i.e. this force is proportional to 1 over r squared. Okay, the universal gravity says the gravity between 2 objects is proportional to 1 over r squared. And then from this, from this assumption and his law of Newton's law of motion, 3 laws, And then Newton can prove that the orbit of a planet is an ellipse. Okay, Newton proved that from math. Now, if you study calculus 3, then calculus 3 you will actually have a chance to study how Isaac Newton derived this. This is actually in the textbook. You can read our textbook for this section. We will not we have no time to explain how Isaac Newton proved this proved Kepler's 3 laws from his gravity theory. Okay. Another remark. Another remark is the following. Okay. Now Isaac Newton, you know, explain Kepler's law. So this unified that thing. So he explained the universe very well on Newton's law. Then I should mention another astronomy, another person, Hooker. Now Newton explained this. Newton know, and at that time, Newton first discovered this universal law of gravity, proportional to 1/r². And this he used that thing to explain how to derive Kepler's 3 laws. And then another person, Hooker. So he is the chair of the Royal Society. Okay, before Isaac Newton. Okay, he is a member of the Royal Society of England, Great Britain. Royal Society member, and he is also has a lot of discovery, and he was named as believed to be the English Leonardo da Vinci. Okay, so this is he is compared with the Leonardo da Vinci. And the only thing, unfortunately for Hooker, is he was born at in the same time as Isaac Newton. Okay, Isaac Newton's discovery is so dominating, so that although Hooker is also genius, but once compared with Isaac Newton, that is really unfortunate. Okay, like the thing you should compare it many superstars, at the same time with Magic Jordan, is a little miserable. They cannot get a championship because of dominating Michael Jordan. Okay, so Hooker also make a claim that he should get some credit with the discovery of this universal, the universal gravity law. And actually, Isaac Newton denied his credit. Okay, when Newton discovered the proof of how to prove Kepler's 3 laws from his gravity theory, several years he did not publish that. And a friend Newton told Newton that Hooker already know this proof, how to prove that the orbit is actually an ellipse from the degree 2 gravity law. Okay, the gravity assumes that gravity is proportional to 1/r². Then Hooker know how to prove that. Then Newton finally published his proof in his book. Okay, then Isaac Newton published his book, this name, Principia. There is now English translation. Now, right now, for people, it's hard to read. For people right now, it's really hard to read because the notation that Newton used in calculus is actually Newton used geometry. Today, the notation that we use is designed by Leibniz. Okay, you see, we have, Newton and Leibniz, they have some dispute between the discovery of fundamental theorem of calculus. The notation that we use today comes from Leibniz. This Newton's book today is hard to read. There are only a few people, maybe very few people can still read without difficulty Newton's book. Now, if you are you think you have a good geometry, you may try to read Newton's book, Principia. Challenge yourself, see if you can read through easily with Newton's book. Okay, then your geometry will be really good once you have no difficulty. Especially, Newton can easily manipulate ellipse. Okay, Newton can easily manipulate ellipse, the geometry of ellipse, conic sections. Okay, the conic section has a long history. Actually, it goes back, ancient Greek mathematicians, near 2000 years ago. Without analytic geometry, it's remarkable that this kind of people study these conic sections and their properties. That's the Euclidean geometry. It's really, really remarkable. And Isaac Newton is, really a great master in geometry. Okay, it's remarkable that Newton did that thing, use geometry. Okay. Okay. Now, after Isaac Newton, Newton theory, after after 200 years of Newton, within 2 centuries, Newton theory is really successful, and many physicists believed that the giant building of physics is already done. Okay, the building is already done. So the remaining thing is we just put a little, put something here, put another thing here. So the foundation is already totally determined. We just put thing on it. Okay, put little thing on it. And however, at the beginning of the 20th century, so at the beginning of the 20th century, Lord Kelvin gave a lecture mentioning that 2 clouds that lies beyond the current theory of Isaac Newton. 2 clouds. One is actually lead to the 2 major part currently. One is quantum theory, and one is relativity. Now, this is discovered in the early of 20th century. Okay, in the early 20th century. 20th century. In the early 20th century. This was discovered. So Newton's law is actually this quantum theory and relativity. The limiting case of this thing is Newton theory. Now, what is unfortunate is this quantum theory and relativity, they are successful in their own right. However, they are not compatible with each other. They are not compatible with each other. So it's a separate theory. Now, what people believe, what physicists believe is a unified theory. A unified theory. Is there a unified theory that can unify this quantum theory and relativity? And there are many trials. Today try to unify this quantum theory and relativity. However, none of them is really convincing right now. So this is still somewhere to be determined. A theory that unify quantum theory and relativity. Okay. Now we have 20 minutes. Then maybe let's do some examples of this of Conic curves. Okay. Examples of example of Conic sections. For instance, R is 1 plus sine theta. Okay, find eccentricity.
We cannot see the screen.
Oh, sorry. Oh, Jesus. Oh. Yeah, maybe I'll just repeat it. Kepler's law. Kepler's law. Okay. Kepler's law. Gravity theory. Okay. Now the general thing is 1 plus E sine theta ED. Okay, so we can actually find here E is 1. So this E is 1. If we compare E is 1, so it should be parabola. E is parabola. This curve is a parabola. Given equation of the directrix. Given equation. Given equation of the directrix. Okay, now we will try to write the thing as polar. From this polar coordinate, we will try to write it as x squared coordinate, Cartesian coordinate. So this will be r plus r sine theta is 1. Okay, so it's r equal to 1 minus sine theta. So r squared will be 1 minus r sine theta squared. R squared is x squared plus y squared. R minus r sine theta is, remember, polar coordinate. R sine theta is y, so it's 1 minus y squared. So y minus 2y plus y squared. So y squared cancels y squared, so this will be x squared is y minus 2y. Okay, if we plot this graph, okay, so this will be y is, so this is the, when y is 0, x is plus minus y. When x is 0, y is 1/2. Okay, so this will be this. So it will be this. Now it will be, remember, we have x squared be 4py, 4py. Then it looks like this. P is negative, P is less than 0. Then this will be, this curve will be looks like this. But then its focus is, this is P. P is negative, this is negative P. Direction is, okay, so this is negative P. So if you compare P, what is P? P is 4py, you get a 2y. So 4p, you get 4p, which is a negative, 4p is negative 2. So p is negative 1/2. P is negative 1/2. So this point should be negative 1/2. This is a 1/2. Now here, we need to translate the thing upward. Translate the thing upward. By what unit? By what unit? Translate the thing upward by 1/2. Translate the thing upward by 1/2. So this is the origin O becomes this thing. This is the 1/2 here. Okay, translate by 1/2. So we can get the directrix here is P. You know, we also need translating by 1/2. Okay. So what's the equation of the directrix? Directrix is L is, so this is the 1/2. And then we translate 1/2 equal to, then translate the thing 1/2. So this is get, we get a 1. The directrix as equation, this y coordinate is, the height is 1. Okay, so this is actually directrix. So we get the directrix. So we get this conic curve. Okay. Okay, more examples. More examples. Okay, let's see this example. R equal to 6 over 3 plus 2 sine theta. Okay, if you, so here, remember, what we write is R equal to ED, 1 plus E. So here is sine theta. Let's use sine theta. So it's normalized such that it's 1 plus E sine theta. So to normalize it, we divide by 3. So R is, divide everything by 3. 1 plus 2 over 3 sine theta. 6 is 2. So we know E is 3 over 2. Okay. So so ED will be 2. So D is, what is D? D is 2 over E. So it's a 3. D is 3. D is 3. Now, let's find its coordinate. Let's find its coordinate. Let's plot the thing. Okay. Okay, now how do we plot the thing? Okay, we may do it use when we do it in Cartesian coordinate, or we plot it directly use polar coordinate. Okay. So let's plot the thing. Let's plot the thing. Okay. So we write it as the thing ED. So we already have E and D. When theta is 0, when theta is 0, what is R? When theta is 0, R is 2. Okay, when theta is 0, R is 2. When theta is pi over 2, when theta is pi over 2, so we know this is an ellipse. E is 2/3. Now when theta is pi over 2, then we get R is 6/4, which is divided by 2, 1.5. When theta is negative pi over 2, what is? Sin theta is -1. So R is actually, we get 6. So this side we get 1, 2, 3, 4, 5, 6. On this side we get a 1/2. 1, 2, so it's 1/2 here. Okay. And then this is an ellipse. An ellipse. So it will be looks like this. 1, 2 by symmetry. When it is pi, we get the same thing. So it will be an ellipse looks like this. Let me insert an ellipse. Okay, it's more or less looks like this. Okay, so this point is 1.5. This point is 2. And this point is -2. And this is 6. -6. Okay, -6. Okay, so you see what is C? What is A? How do we find? So what is 2A? 2A is the longest axis. Okay, 1.5 and -6. And then they sum to 7.5. So it's 6. So 1.5 minus -6. -7.5. So A is, so this is the 15/2. So this A is 15/4. Remember, E is, what is E? E is C over A. C over A. Now this will be 3/2. 3/2. Now what is this? So A is, so C is 2/3 of A. So 2/3 of 15/4. So this will be 5 times 2 over 4. So it's 5/2. Okay, so 2.5. C is 2.5. So we can write down the equation. Okay, so it's 5/2. So we can also find a B squared. So B squared. So B squared will be A squared minus C squared. So the 15/4 squared minus C squared, 5/2 squared. If we factor out the 5 squared, so it's a 5 squared, 3 squared over 16 minus quarter. So this will be 15/5/16. Okay, so it's equation. We can write down its equation. Now it's translated. So this curve we also translated. So it's A is along the y-axis. Okay, A is along the y-axis. So it should be looks like this: y squared over A squared plus x squared over B squared is 1. But here, we already get B squared. And then we get a squared, but we need to translate the thing downward by how many units? How many units? By how many units? How should we determine what translation that we should get? Okay, this will be 3.75. 3.75. Then now it becomes 1.5. So it's so we translate downward. So translate downward by how many? How many units? 15 over 4 minus 1.5, 3 over 2. Okay, so this is actually 9 over 4. 9 over 4. Translating by downward. Okay, so it should be y, plus or minus. Y plus or minus. Plus or minus. Y plus 9 over 4. Over a squared, remember a squared is 15 over 4. And then plus x squared over b squared. B squared is 1 over 25 times 16. This equals 1. This is the Cartesian coordinate of this. This is the Cartesian coordinate of this polar axis, polar equation of this curve. Okay. Okay. Now the general routine to do this kind of problem is try to pick out some special theta. Try to plot this curve. Okay. First conclude whether it's find E, and then conclude whether it's parabolar, ellipse, or hyperbola, and then find the parameter ABC. Okay. And then plot this curve according to these parameters. Sometimes we need to do translation. Okay, we have 2 minutes. Maybe we don't have enough time to another example. Let me just stop here.